Hello and welcome to day 2 of daily Leetcode challenges. Let's begin our question. Okay. Question 652. Find duplicate subtrees. Given a root of a binary tree. Okay. Return all duplicate subtrees. For each kind of duplicate subtrees, you only need to return the root node of any one of them. Oh, so if a duplicate is found, then either this root of the subtree is returned or this root of the subtree is returned. Two trees are duplicates if they have the same structure and the same value and the same node values. Okay. So, okay, so what if they have consecutive? So why is this 4 not covered? Is my question, right? Because this is one node a subtree? It is. One node is a subtree. So maybe this should be covered as well. Maybe it's just not. I don't know, weird scenario. But anyway, regardless, this sounds like a Merkle tree problem. In a Merkle tree, you kind of preserve your subtree's state in a hash, and therefore any change to the child results in a change of the hash. So for example, let's start with the most bottom node. This tree, which is a tree, this node is going to have a hash of its children. This node is going to have a hash of itself and its children. This node is going to have a hash of itself and its left child, which is 4, and its absent right child. So is this one, and so on. And since the hash of this subtree, which is the left child 4, itself, and the absent child, and the absent right child, since this subtree is going to have a hash, and this subtree is going to have a hash, the hashes are going to be the same. So essentially we can just keep track of, we can have a dictionary where the key value is just the hash of any subtree, and the value, the node itself, I guess, right? The node, the root node of that subtree. I'm pretty sure that that's yeah. So that's called the Merkle tree. We have a, let's define Merkle as a function that takes the root. Okay, so what are the two? Merkle left. It's going to be Merkle with root left. And let's have another root right, where we have a root right. And the Merkle, the hash of its own, is going to be, let's say, it's going to be the hash of Merkle L plus node value. So we're keeping track of it, of ourself, and Merkle R. Sorry, Merkle R. Then let's tracker H, append node, and return H. So this is a recursive definition of how we're going to sort of design this Merkle tree. Again, the very basic explanation is that we taken a root node, and the hash of our node is the hash of the left node, the hash of the value, node value, and the hash of the right node. Assuming that the child hashes are the same, or sorry, assuming that the child hashes are defined in the same definition, if our current hash is the same as some other hash in the tree, then we know that the subtrees of those two nodes are identical. So we, I guess, also need a tracker with collections default dict. Let's have a list here. Right, miracle L, miracle R. We're gonna call miracle on the root node. Let's call this node, I don't know why called this, and then, okay, so since we're appending this, we're gonna say that return. Okay, so what do we need to do? We need to return the okay, quick look back at what we've actually just done. We have a tracker, which is a dictionary of key value pairs, key being the hash of a subtree, value being the nodes. And since we don't care about which node to return, if we have, let's look at any constraints. Number of nodes, value doesn't matter, and there's nothing weird in the constraints that would prevent us from doing this. We have a dictionary with key being the hash of a subtree, value being the nodes that are the root nodes of that subtree. So all that we really need to do is we need to say return, let's say roots 0 for roots in tracker values. Tracker values. Okay, maybe also one thing that I might have forgotten is I forgot to have a base condition. Base condition is when I end up hitting the leaf node. So if not node, return some odd number. So essentially what our hash is going to look like for, let's say, this 2 is it's going to be some weird hash, hash L, plus, let's have this be, I don't know, a $sign. Then it's going to be a $sign, and it's going to be hash R, right? Hash, let's say 4, hash 4. This is going to be our, sorry, no, this is not, it's going to be hash of 4 equaling, actually, hash of 4 in itself equaling $sign, then 4, and $sign, and then I have another $sign, which is me. Okay, one more time. Let's define the Merkle hash for the node of value 4. Node of value 4 is going to be a $sign, 4, $sign. So this is for 4. For these 3 nodes of value 4, I'm going to define here. Let's see what for 2 is going to be. For 2, for these 2's, it's going to be the left node is $for $. The value itself is 2, and then the right node is $. Right? And so on. And since this hash is going to be the same for both of these nodes, all that we need to do is take the first element out of that node, if roots if len roots is greater than 1. Right, so if we have a duplicate, if they have the same structure, the same nodes, two trees are duplicates. Could there be 3? I'm thinking there could be 3, definitely, but it doesn't seem like there's an example for 3, even though this should serve as an example. Okay, let's submit this. Looks good to me. So a quick explanation. Maximum recursion depth exceeded. I am if not node. I am passing in root instead of node. Sweet. So now just Merkle L is not defined. Merkle oh, sorry. And hash not defined, you can only concatenate strings. These are strings. This is not a string. Let's have this be a string. Unsupported for int. How is this an int? Unsupported operation type for int and string. Which one of these is an int? Print Merkle R. Should be the same. $. Oh, the hash function itself is a number. So we actually, I guess, do need to say that these are strings, not hashes. Or a more proper approach would just be to stringify this guy. And now all of a sudden, we are returning a string. Okay, run. Sweet. Awesome. Beating pretty much everyone. 96 percentile. This is not bad at all. Yeah, Merkle trees are there to sort of prove that the history, which tend to be your children, the history hasn't changed or wasn't tampered with. It's actually used in cryptocurrency. Also, Git protocol uses this. I mean, maybe we can check out some other solutions, but I don't think that they are. Yeah, they're not really providing anything significantly different. You have the rest. Yeah, so I mean, they're constructing the result quite differently. Their result is what is populated inside of the traverse, which could speed up the process, but kind of like having that count where a counter where the traversal is essentially holding the key value pairs of keys, and the keys being the hashes of the nodes, and then the value being the nodes themselves. And yeah, I think that's very intuitive. Okay, so yeah, I would suggest just using this memory. There's absolutely no difference between the best solutions and ours. So yeah, okay, sweet. Thanks for watching. See you later.